Assalamu alaikum students. This is our lecture 15. Now basically in this lecture we find out the relation between magnetic moment and Bohr magneton. What is magnetic moment? Basically in the case when an electron is revolving around the nucleus, we know that the electron is a charged particle, and on the atomic scale all matter consists of atoms. We know that all matters consist of atoms which contains electrons, and that electrons are circling around the nuclei in different allowed orbits. So it means that these electrons are possessing both orbital and spinning motion. So basically electrons are moving around the nuclei or nucleus, and they are also spinning around their own axis. So it means that both orbital and spinning motion produce magnetic effects. Basically in this case we have magnetic moment, because when any charged particle is orbiting or spinning, then it means that there is a current. So in this case when we have magnetic effects, we discuss magnetic moment. And the orbital motion of electrons produces atomic current, which is purely circulatory, giving rise to no net charge transport. So it means that each atomic current constitutes a current loop of atomic dimensions and behaves like a magnetic dipole, with one face as north pole and other face as south pole. All magnetic effects of matter may be understood on the basis of three of these magnetic dipoles. So the magnetic moment of a current loop behaving as a magnetic dipole or orbital magnetic moment of electron is given by. Now basically we discuss here that if we have a charged particle, then due to the motion of the charged particle there is a current. So it means that this current is due to the magnetic effects. So we have magnetic moment here, and that magnetic moment is equal to current multiplied by area of loop, that is IA. So if an electron E traverses the loop in time t, now basically we know that current, what is current? Current is equal to Q by T. So here we have electron, so we write E. If an electron of charge E traverses the loop in time t, we have E is equal to E, I is equal to E by T. So putting this value of I in equation 4.47, we have mu L is equal to IA, and that is EA over T. Now here we discuss the aerial velocity of electron. Why we discuss the aerial velocity? Because when the electron is orbiting around the nucleus, there is the angular momentum. And in the case of the law of area, of Kepler's second law, you discuss it in studied it in mechanics 2 course. I don't know you study it or not, but you have to check it in the chapter gravitation on I don't know what is the chapter number, but you can check it from the Kepler's second law, that is the law of area. So that law defines that the aerial velocity of any object which is circulating, which is orbiting around the nucleus, is equal to, here we discuss the electron, there we discuss the earth is moving around the sun, here we discuss the electron is moving around the nucleus. So in this case we discuss here D, that the electron, sorry, In this case, we have dA by dt, that is that is dA by dt, that is the law of area, that is dA by dt is equal to L over 2m. If we take the time 0 to t, because we say that the time is of moving of electron around the nucleus is 0, starting from 0 and goes to t. So we integrate it from 0 to t, that is L over 2m dt, and from here we have L over 2m capital T, and we apply the limits. So from here we can find out the value of T, that is 2ma over T. So putting this value on equation 4.48 we get in the last equation, that is in the last equation we have this this is the equation, that is 4.48 EA over T. Putting this value of T in this equation, we have this is the result, that mu L is equal to E over 2m L. Since orbital angular momentum L is quantized in quantum mechanics, we know that we have L is equal to L under root L plus 1 h over 2 pi. Now if this value is approximately this value, this is very small, because L plus 1 under root is very small value, so approximately we can take it LH over 2 pi, that is LH cut approximately, where L is the orbital angular momentum, orbital quantum number. The combining equations 4.50 and 4.51, we have mu L is equal to E over 2m. Here E over 2m, I am putting the value of capital L, we have LH over 2 pi, and from here we have LEH over 4 pi m, LEH cut over 2m. So it follows that orbital magnetic moment is, this is the orbital magnetic moment. So orbital magnetic moment is directly proportional to L. That is, thus mu L is equal to 0 if L is equal to 0. Mu L is equal to EH over 4 pi m if L is equal to 1, and mu L is equal to 2EH over 4 pi m if L is equal to 2. So we know that the orbital magnetic moment is an integral multiple of the quantity EH over 4 pi m, that is EH cut over 2m, known as Bohr magneton. So this value is equal to Bohr magneton. So this is the equation 4.52. 4.52 establishes a relationship between orbital magnetic moment and spin magnetic moment. The spin magnetic moment, both atomic and subatomic, are expressed in terms of Bohr magneton. The spin magnetic moment of electrons is 1 Bohr magneton. So in this case, we discuss here this is the Bohr magneton. You can see EB is equal to EH over 4 pi m. Mu B is again equal to EH over 4 pi m, where as mu L is equal to EH over 4 pi m, that is EH cut over 2m. Its value is 9.27 into 10 raised to power minus 24. Expressed in joules meter square per Weber or ampere meter square in SI units. We can define, we can also define here the magnetic gyromagnetic ratio G. both for the orbital and spinning motions of the electrons as follows. That is orbital. When we find out the ratio between the orbital magnetic moment and orbital angular momentum, we say it as gyromagnetic ratio G. That is the magnetomechanical, we say orbital magnetic moment, and the ratio between the orbital magnetic moment and orbital angular momentum, that is mu L over L. From equation 4.5 we have mu L over L is equal to E over 2m. Similarly, G spin, that is the spin magnetic moment over spin angular momentum, that is equal to mu B over half h cut. So from here, since spin moment of electron is equal to half h cut, from here we have GE h cut over 2m, half h cut is equal to E over m. So combining equations 4.53 and 4.54, we get G spin is equal to E over m, 2E over m. So it means that G spin is equal to 2G orbital. Clear? Students, this is the discussion, this is the necessary formulas of related to Bohr magneton. So you know that in this case we discuss that the Bohr magneton is equal to EH over 4 pi m, and in the last case that basically this is the Bohr magneton, EH over 4 pi m, mu L is equal to LEH over 4 pi m, and it means that when we apply mu L changes, when we have L is equal to 0, L is equal to 1, and L is equal to 2. So orbital magnetic moment is an integral multiple of the quantity, and that quantity is called Bohr magneton. So mu L is equal to EH over 4 pi m, and mu B is also equal to EH over 4 pi m. So this is the brief introduction of the magnetic moment and Bohr magneton. So we completed this chapter now, and the other topics, that is the Stern-Gerlach experiment, that is this Stern-Gerlach experiment, we will not discuss this topic. This is the last topic, that is the Bohr magnetic moment and Bohr magneton. Now this chapter is finished, and next we discuss the chapter number 4 in next week, and also I will take quiz of this chapter 3 in week number 6. Thank you, students.